Good morning, everybody. We're just going to wait another minute or two. We're missing about half the class for some reason, so we're just going to wait another minute or two to see if any last-minute stragglers will be joining us. Otherwise, we'll get started. All right, we're going to go ahead and get started, and hopefully everyone else will join us shortly. So good morning. It was nice seeing you guys again yesterday. The plan for today is to finish up yesterday's notes and to finish up the greatest integer function. After that, we're going to start a quick review on the exponential function and do a couple of little new pieces with the exponential function, starting today, finishing up tomorrow. So we'll be taking a look at that. Before we get started, are there any questions on any of the previous assignments or handouts that you'd like to go over? I'll take a minute while I'm setting up the screen share. Take a minute either verbally or just typing it into the chat to see which questions that you'd like to go over. As of now, I don't have any questions in the chat. Don't forget to open up the chat first and foremost. And as of right now, I don't have any questions that are being asked. Is there anything that you want to go over before we jump right into the new material? Okay, so there was a mistake in just before we get started. There was a mistake in question 1 for class 7, the quiz, the Google Forms. So if you want to go in and resubmit that just to make sure you do understand, please feel free. There's a little bit of a typo error there in assignment 7, so I noticed it yesterday and I went in and fixed it. So feel free to resubmit if you're not getting it right or you just want to try it again. Whatever the case may be, you can resubmit that. Get started on that. I think what we'll do is we'll start off with a problem from the assignment, just to make sure, just to like kind of wrap up the square root function idea, and then we'll go from there. So I'd like to take a look at number 3 of the assignment. Okay, so number 3 of the assignment says the function f shown below describes the height in meters of a kite as a function of elapsed time since launching the kite, and then you're given this piecewise function. So in this problem, again, this is assignment 7, number 3. So you're given this piecewise function, and the piecewise function involves square root functions as well. So it says the function is given, you have a picture of it, you have the 3 different functions. The kite is 40 meters off the ground after 4 seconds after its launch and falls back to the ground 12 seconds after its launch. How long in seconds was the kite at least 10 meters high? So what we need to do here is we need to find out the 2 instances that it was 10 meters high and subtract those 2 times. The only issue is we don't have any of the parameters for the 3 functions. So the first function is a quadratic, the second one's a square root function, the third one's a line. So we need to find the parameters. So if we work with rule 1, we have the point 4 and 40. So we're going to plug that in order to be able to find the parameters that we are missing. So 40 equals 16a, and if I divide by 16, I get that a is 5/2. So rule 1 actually looks like y equals 5/2x squared. 2. Rule 2, we also have 4 and 40. So we have y equals the root of bx So there's a question in the chat saying, can you screen share yourself doing a problem? I am. Do you not see me writing? Is there an issue? Can everyone see me writing? Okay. Okay, just to make sure. Thank you guys. Okay. So here I can plug in 40 equals b, and we have 4 here. So I'm going to square this. So 1,600 equals 4b, and I can divide by 4, giving me 400 is my b. So that's my second rule. Step 3, I need to find the point. I need to find the point B. So I'm going to be plugging in x is 9 because that's the flip over point from one function to another. So I have 400, I have 9. So 400 times 9 is 3,600, and if I square root that, I get 60. So I have 9 and 60 as a point on both the square root function and on the line. So what am I going to do here? Well, now I need the equation of the line as well. So step 4 is going to be line, so that's function 3. So I have y equals, they use c, x, and d, doesn't really matter. But I have points 9 and 60, and I also have point 12 and 0 from the fact that it hits the x-axis at 0. So I'm going to get my slope, or I'll guess this should be called c. So c is y2 minus y1 over x2 minus x1. From there, I have 0 minus 60 over 12 minus 9. That gives me negative 60 over 3, which is negative 20. So y is negative 20x plus d. And then I can plug in whatever I want. So 0 equals negative 20, 12 plus d. So if I do negative 20 times 12, I get 0 equals negative 240 plus d. So 240 is my d. So the last one has a rule, negative 20x plus 240. Now I need the two instances when the kite passes at 10 meters. So if you're visually looking at this, you see that it's going to hit 10 meters at two different points. It's going to hit 10 meters on the quadratic function, the first one, and it's going to hit again on the third one. So the square root function for that piece of it never goes at 10. Okay, so we're going to do y equals 10 for function 1. So in that case, we have the rule now. So we have that it is 5 over 2x squared. So 10 equals 5 over 2x squared. I move this up. 20 equals 5x squared. And divide by 5, giving me x squared equals 4. And I square root. So x is 2. So after 2 seconds, it reaches a height of 10 meters. And then I'm going to plug in y equals 10 into function 3. So I have y equals negative 20x plus 240. 10 equals negative 20x plus 240. If I move this over, I get negative 230 equals negative 20x. And I can divide by negative 20. That gives me 11.5. So the two instances that it reaches a height of 10 meters are 2 and 11.5. Now, the only added thing that we have to be careful of with piecewise functions is that when I work backwards, I have to make sure that this value is in my domain. So function 1 is between 0 and 4. So 2 fits in here. That's good. Function 3 is between 9 and 12, and 11.5 fits in here. So we're good to go. So the time that we are looking for is 11.5 minus 2. So that's 9.5 seconds that it spends at least. That it spends at least, that it's at least at a height of at least 10 meters. Okay, so that's a kind of, you see how many steps I just did? That many steps means it's a 10-point question. So you can expect something like this in a part C because it puts all of the functions together. So you're using quadratic, you're using linear, you're using square root function, you're using piecewise function. and you're putting them all together. So you could get this in a 10-point question. So it's really, do you understand the parameters for all the different types of functions, and can you use them all together? Okay. Is that good for everybody? Okay, cool. So if we're ready to move on, no other questions, that's fine. I'll wait a second just in case there's another question that you want to go over. No? All right. So just a quick recap of what we did yesterday. We finished the square root function, and from there we started talking about step functions. So the first couple of things that we did were review of what you had done last year or during the year. So essentially we have these step functions that are horizontal pieces putting together to make one big function. So during the year or last year, depending on your case scenario, you either had to read them. For the most part, it was just reading, or specific word problems where you drew, for instance, like the one we did here, you drew the sketch in order to be able to answer the question. So then we said, okay, well, there has to be a better way of doing this. There's rules for everything. Why wouldn't there be a rule for this? So there is, but we had to talk about the idea of a greatest integer before we could move on from there. So the idea of a greatest integer, again, is that we are choosing the integer closest to my number without going over. So essentially we're dropping backwards to the integer just behind our number. So for positive numbers, that means I just take away the decimal portion. And for negative numbers, it's I drop backwards. Okay, well, for both it's drop backwards, but you just have to remember that you are dropping backwards. And for negative numbers, you can't just drop the decimal. We talked about working backwards quickly, where you have to have a whole number equal to the greatest integer bracket or there's no solution. And when you have the greatest integer bracket equal to something, there's going to be an interval of x's that give you that specific value. So we're going to take a look at an easy way to, or an easier way to solve this than just having to do the bracket yourself when we start doing more complicated problems. So then we started talking about the basic greatest integer function and what it looked like. So the base case y equals greatest integer of x. We graphed it. We talked a bit about step length, counter step, and all of that kind of stuff. And we talked a little bit about the properties and how it's a little different because it jumps a whole bunch of different y values. So it's not every y value. You actually have to skip over a whole bunch of different y values. Okay. So then, of course, when we have a basic function, we also have a transformed function when we're introducing different parameters that influence the picture itself. So we have these parameters A and B that we deal with. So they do play two different roles, and then they play a combined role. So A is the distance between the steps, how far apart the steps are, which we use the term counter step. B determines the length of the step. It has an inverted relationship. So whatever B is, we just flip that number, and that's going to be our step length. B plays its individual role where it decides whether or not the step is closed to open or open to closed. And then they play a combined role where if they are the same sign, we have an increasing function. And if they are opposite signs, then we have a decreasing function. So they play individual parts, and then they play combined parts. So the last thing we did was graphing. So we placed a solid dot. You have to place your solid dot at 0, 0. You have to do your analysis when you're graphing. So you need certain pieces of information that you're extracting from the rule to be able to know what your picture should look like. So you're looking for step length. You're looking for whether or not it's closed to open or open to closed. And you're looking if it's increasing or decreasing. So these are the things you have to analyze from your rule, and then you can sketch. You put your point at 0, 0. And you start from there. Either you extend your step to the left or to the right but everything you do is determined from your analysis. So whatever B is, that's going to determine what your step looks like. Whatever B is also gives you step length. And A and B together give you increasing, decreasing. So that's what we finished off at. So we graphed 3 different functions. So we have come to finding the rule given a picture, and then we're going to move on to word problems. So take a quick minute. So you're missing the blue. Make sure you're copying down the blue right now. Okay. So we had to do an analysis from the rule in order to be able to create the graph. We're going to be doing a similar analysis from the graph in order to be able to create the rule, because we need all the same pieces of information. So we know that the distance between steps is A, and the length of the step, we just flip it to get B. Based on if it's increasing or decreasing, that tells us whether or not A and B are the same sign or opposite sides. And the way the step is oriented, either from open to close or close to open, that tells us a sign of B. So all of these different things go together to give us the rule. So we'll take a look at what this looks like. So if we have this picture, we're pulling out different pieces of information to help us create our rule. Okay, so we'll start off with A. So if we look at A, we're looking at the jump between steps. So this first step is at 2. The next step is at 4. So I'm jumping from 2 to 4. Sorry, not very good. We look at the step length. So I have 1, 2, 3, 4, 5, 6. So my length is 6. So B is 1/6. My step is close to open, so B is positive. It's increasing, so A and B are the same sign. So B is positive. That means A is positive as well. So just for the purposes of this class, like I said, normally we have our solid dot at 0, 0, but we're just going to, based on these pictures, just do a quick analysis of the AB increasing, decreasing. So in theory, we would have the 2 and the 1/6x. Because this doesn't start at 0, 0, we do have something else to work with, but we don't have to deal with that. So I just wanted to go through the A and B analysis. So that doesn't change. You'll never get something that doesn't pass through 0, 0. Okay. We'll do the same thing with this one. So like I said, even though it doesn't start at the 0, 0, we can still do the AB analysis to give us the AB parameters. So we're going to say that the counter step. So the jump we are making from step to step is 1, 2, 3. Step length is 1, 2, 3, 4. So B is 1/4. The step goes from open to closed. That means b is negative. So b is actually negative 1 over 4. The function decreases. So a and b are opposite signs. So remember, you're referring to your chart. So if b is negative, that means that a is positive. So a would be positive 3. So that is the analysis that you're doing. And since you only need a and b for your rule, you would just create it with a and b. Any questions? So counter step, step length, b, increasing, decreasing, and then you determine your signs. Cool. So just a quick overview of what the properties look like when you have the parameters introduced. So the properties always are really strongly related to the parameters. So parameters A and B in this case. Okay, so we're going to take a look at this. The domain is always all real numbers. So when you have this greatest integer function, you never see a part of your picture where you're just skipping over x values. So you can always plug in the x. The y, the range, has to do with what a is, because a is our counter step. So it tells us how many, what our jump is going to be, and therefore how many integers we skip over. So am, where m is an integer. So for instance, if your a is 3, then your range would be 3m with m as an integer. What this means is you have different possible y values, and they're all multiples of 3. So you'd have -6, -3, 0, 3, 6, 9. So those ... in both directions because it doesn't stop, but those are the different y values that we can take. We have the counter step being the absolute value of a, so there's the value because we can't have a distance that's negative, so we just say it's the positive a. The y-intercept is 0. The x-intercept, so when we were graphing, we always had a step that was on the x-axis. So our x-intercepts really depend on what that step looks like. Positive, negative also really has to do with this part of it and whether it's increasing or decreasing. Here we have the increasing, decreasing, so we understand that with step functions, either I'm increasing or I'm decreasing, but I'm never doing both. So we are increasing always if A, B is they're the same sign, right? But we're never increasing if they're opposite signs. And it's vice versa for this part. If it's decreasing all the time if they're opposite signs, and it's never going to be decreasing if they're positive signs. So this, again, is not one of those things that you have to memorize. You may get a question in like a part AB. It gives you a rule and it says which of these properties are true, something like that. It's not super likely, but it is a possibility. But if you understand the properties, then you should be able to do this regardless. Questions? Okay, cool. Okay, so before we can start doing word problems, we have to know how to solve backwards. So we took a quick look at what this looks like. So if we have a y and we're solving for an x, it's a slightly different method than if you're just solving forward. So we'll take a look at this. Before we can get into word problems, we'll have to learn how to do this kind of solving, and then we'll go into it. So take a minute to write down the blue, and then we'll start the examples. So there are two different ways of doing this. I'm going to show you one of them. The other one's a little bit mathematically messy. So we're going to just look at this one for now. But if you're really confused and say, I really have no idea how to do this, let me know and I'll show you quickly the second method. Okay? Are we ready to go? Any objections? Okay. So the first example is you have this. This is your A and this is your B. You have this greatest integer function and you're solving for when y is 25. So what I'm going to do is I'm going to plug in 25 for y. Now step one says I have to isolate the greatest integer bracket. So I need to divide by 2. I actually want to do this problem. Let's just change this quickly to 26. If we had kept the 25, just so we know, you would have gotten 12.5. And if we remember from yesterday, when you have a decimal, this gives you no solution, right? Because you can't have a decimal equal to the greatest integer bracket. So I do really want to go over this, so I'm just going to change this to 26. That way we don't run into that issue. Okay. 26. So I do divide by 2 because I'm isolating the greatest integer bracket. Now, step 2 says drop the greatest integer bracket and just solve the equation. So I have 13 equals 0.2x. So if I divide by 0.2, I get 65. So as we know, when we're working backwards, we should be getting some sort of interval, not just one point. So what we just solved for is our solid dot on the interval. So now we have to somehow create the step, knowing that this is our solid dot. So we're actually going to do an analysis. So we need to know information about the step. So first, we have that B is positive because it's 0.2. So our step goes from solid to open. The other thing we need to know is length. So B is 0.2. So just so we know, that's 1/5. So my length is 5. So based on that, we know that this is 65. We know that it's the solid dot, and we know that this should be the beginning. 6,5, 65. But if we know that the length goes, it's 5, then I just add 5. So this goes to 70, and this is the end of my length. So we just did 65 plus our length to give us the other side. So you're solving, you isolate the greatest integer bracket, you drop it, pretend it's not there, and just solve your equation. That represents your solid dot on the step. Then you do a quick analysis of information regarding the step, so the length and the direction, and then you can create your bracket from there.
Miss, where do you get 1 over 5?
0.2, I just changed it to a fraction.
Okay, thanks.
You're welcome.
Yeah, but Miss, where did you get 0.2 out of 26?
The y is 26, but my b is 0.2. We look in the equation.
Oh, this is, oh yeah, okay.
Okay, so let's take a look at another one. All right. So we have -8. So we need to isolate the greatest integer bracket. How did I get a length of 5 before we continue? So 0.2 is 1 over 5. So I flip that. So this flips to become the length. So b and the step length are flips of each other. They're inverses of each other. Okay. So here I'm solving. So I'm going to divide by -0.2. That gives me 40. Step 2 says to just drop the brackets and solve. So 40 equals 8x, and I divide by 8 to give me 5. So now I'm going to do an analysis of the step. So I know that, I'm pretending this isn't here, b is positive, meaning I have a step that's solid to open. So this is the beginning of my step. b is 8, so the length is 1 over 8. So to get my end, if I start at 5, I need to add 1 over 8 to get my endpoint. So 5 plus 1 over 8. If you do this on your calculator, you have a choice. You could either do it with the fraction button or not with the fraction button. So that gives you 41 over 8, or if you prefer 5.125. So we would say this goes to 5.125. Not too bad. Questions?
How did you get 1 over 8?
So 8, so here the b is 8. So
Oh yeah,
that's
you flipped, okay.
Yeah, 8 over 1, so I just flip. Okay. So here what I'm going to do is I want to do a different type of example. So just add a negative in there, just so we actually cover the last case. Okay. So now the question is y equals -3 in the greatest integer bracket, -0.25x, and we're solving for when y is -54. So let's try this one out. So we plug in our y value. I'm isolating the greatest integer bracket. So that gives me 18 equals -0.25x. My next step is just pretending the brackets aren't there. And I divide by -0.25. And that gives me 72. So that is my solid dot. Now I do my analysis. So b is negative, meaning my step goes from open to closed. So this is actually the end of my step. B is, I don't care what the sign is right now. I've already looked at the sign. So B is 0.25. That's the same as 1 over 4, right? We could just write that. Negative. Negative on the 72. So the length is 4. So since this is the end, I want to find the beginning. So if you do negative 72 minus 4 is negative 76. So the beginning is negative 76 and negative 72 is the end. So how do we feel about this? Any questions? So this that we saw, the question is, how do you know if it's the beginning or the end? So when you solve, when you drop the brackets, whatever number you get, that is the solid dot. So you look at B. If B is negative, it goes from open to closed, meaning that the solid dot is at the end. So my number that I solved for here goes at the end. But if B is positive, and number 2, B was positive, so the solid dot is at the beginning. So the number that I solved for here, this 5, goes at the beginning. So this is a tool that we need to do the word problem. So what we're going to do is we're going to jump into word problems. And then when we're solving the word problems, we're going to be using this tool. So we'll probably see another 3 or 4 examples, at least 2, maybe 3 or 4 of doing this anyway. So we'll move on and then we'll still see how to solve this properly. Okay. So let's take a look at word problems. Okay, so here's what you're going to do for word problems. So the word problems that you get are the same type of word problems that you saw last year, but we're actually going to create the rule instead of having to graph the whole thing. So we do have to sketch the situation just to help us with the sign of A and B, but you don't have to have a full, really good sketch, and you don't have to continue so that you see your answer. It's just going to help us build the equation. So you have to start off by defining your variables. So X is this, Y is this. Then you need to sketch the situation. Just do a little sketch just to see, it helps you understand the situation a bit better. And from there, we can decide if A and B should be positive or negative. In the question, it'll tell you an A value. So it's a jump in Y. So wherever the change is in Y. Then in the sentence, it's going to say B, so the length of time that we're staying at a given value. Then we have to decide the signs of A and B, and then we can use our equation to solve. So the question is, let's say you're really stuck on the problem. Can you just draw a graph to find the answer? Yes. The only case scenario where you would get stuck, or it would be maybe more of an issue or a pain, is if your answer is really, really far and then you have to make this huge sketch to be able to answer the question. Then it can be a bit of a pain in the butt. But in a part C question, if you decide to do it that way, that's fine. The only thing is in a part A question, if they give you a scenario and say, what is the rule of this function, then you don't have a choice. So it honestly just depends on how the problem is presented to you. So you do have to be familiar with this, because if they give it to you in a part A or part B question, you have to do it that way. Okay, so let's take a look. A sales clerk makes $4 for every 50 of merchandise sold each week. So we're not going to represent this situation graphically. We're just going to do a little sketch. So the first thing it says is to give X and Y. So here my X would be dollars of merchandise sold. And this would be my profit or my salary. So now, just to help you understand what is happening in the problem, just on the side, draw a quick sketch. So if I don't sell anything, I make $0. How long do I make $0 for? Well, when I hit $50 worth of merchandise, I'm going to jump to 4. And then when I make $100 worth of merchandise, I'm going to jump to 8. So now we kind of understand our situation. So in this case, I have that A is 4, what I'm jumping by. My length is 50, because that's how long I'm staying on that step for. So my B is 1 over 50. My step goes from closed to open, so B is positive. And I'm increasing, so A and B are the same sign. So what this gives me is Y equals 4 X over 50. With the A positive, because the B is positive here, and A and B are the same sign, we have them both as positive. The question is, isn't it open to closed? It is not, because you don't make the $4 until you get to 50. So you're at 0 until you get to 50, and then you jump to the 50. And then you still only make the $4 until you jump to another 50. So when you get to 100, then you make it to the next step. So it's closed to open. Yes, it is. So you can write this 2 ways. Either you could say 1 over 50x, or you could just write it like this. Either one is fine. So the question is, how much merchandise would he have to sell to make 144? So once we have the rule, we use the rule to answer our question. So this is the skill that we just learned. So we divide by 4. We get 36. The next step says we drop those brackets. So we have 36 equals 1 over 50x. And we bring this up. And we get 1,800 is my x. So once again, this is my solid dot. But now we've already, in order to create the rule, we've already done this analysis. So now I'm just going to make my step. So the solid dot is at the beginning. The length is 50, so I'm going to add 50 to get to the end of my step. So if he sells between 1,800 and 1,850, not including the 1,850, then he'll get $144 for himself. Now, this is an example of where it would be a big pain in the butt to try to answer this question with a graph. Because in order to answer this question, you would have had to have graphed this so that you get to 144 on the y-axis. So this is going to take your whole page and a whole lot of time. So it's not impossible, but this saves a lot more time than trying to graph it to the point where you can see the answer. All right, let's look at number 2. Monica is checking out a cell phone plan. She finds out that finds one that charges 10 cents for every 2 minutes or part thereof. So if we draw a quick sketch of this situation, so just for clarity's sake, and is free for under 2 minutes. So just add that on just for clarity's sake to make sure we all understand the situation and we're creating the same rule. So the question is, why don't we just do 144 divided by 4 and then 36 times 50? That's, yeah, you can, but then you need to be able to create your step. So you have to be able to do that somehow, because if you just put 1,800, you don't get full points. That's the only issue, right? Okay, so let's do a quick sketch of this. So it said it is free for the first 2 minutes. It's usually impossible to get a negative world problem. So you're usually just graphing in the positive sense. Here, if we don't use our cell phone, we don't pay anything. So this is our, oh, we forgot to define our variables. So X would be the minutes and Y would be the cost. So if we don't talk on my phone, we don't pay anything. How long do I not pay anything? Up until minute 2. Then it jumps to 10 cents. And I stay on 10 cents up until 4, this being an open dot. I know it's a little hard to tell when the pen looks like this. And then at 4 minutes, I would jump to another 10. So we have 2 steps. We pretty much know what we should be doing. So the counter step is 0.1. The length is 2. Meaning my B is 1/2. My step looks like this, so my B is positive. And my function is increasing, so A and B are the same sign. So from there, I make my rule, y equals a b to the x. So they're the same sign. So here I decided that b is positive. A and b are the same sign, meaning that a is also positive. So y is 0.1, the b is 1/2 x. Now it says if she has $3.10 left on the phone, how long of a phone call can she make? So I plug in the 3.1 and I solve. So I divide, we'll just divide here. So 3.1 divided by 0.1 gives me 31. So I drop the brackets. I'm going to multiply by 2 to give me 62. So again, I know that this is my solid dot. I know that the solid dot is at the beginning. I know that my length is 2. So I'm going to add 2 to get to 64. So if she has $3.10, she can talk for between 62 and 64 minutes, but not including 64. Because as soon as she talks for 64 minutes, she would jump up in price. So again, this is one of those case scenarios where you could answer this with a sketch, but your sketch would have to be humongous and probably take up a lot of time to create.
Miss?
Yeah.
What's the difference between what's a counter step?
Okay, so the difference is you can, but you can't. So you can't just say A is 0.1 because it could be positive 0.1 or it could be negative 0.1. So when we're saying 0.1, we're calling it the counter step. The counter step is jump from step to step. So what is the distance between the steps? And then once we've made our decision about B, the sign of B, and whether it's increasing or decreasing, then we could say the sign of A. Okay, let's do another one, just to make sure we're feeling okay with this. Okay. A sugar refinery charges $2 for every 100 grams or part thereof of sugar to be shipped. So X would be the grams of sugar. Y would be the cost for shipping. So if I do my sketch, dun, 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 dun. I'm just going to change this so we can just look at something different. Sugar refinery charges $2 for anything under 100 grams and $2 for every additional 100 grams or part thereof. We'll take a look at what this would look like, because this problem, if I state it in this way, is going to be a bit different for us. So I want to take a look at that one. So just if you want to do the change quickly. Okay, cool. So now we're going to do our sketch. So we called this grams and we called this cost. So up to 100 grams says anything under 100 grams is going to cost us $2. So under 100 grams is going to cost us $2. But at 100 grams, we're going to jump up. Oh, this question's a little bit dicey. I just want to make sure I word it in a way that is very clear for us what we are doing. Okay, we're going to scrap this problem just because I find it a little bit vague and I don't want to confuse you with identifying your parameters. So just scratch it. We'll go to number 4. The cost of parking a car in a garage is given by the rule. You have this rule here. You have your parking time and you have your cost. In what interval, if this is the parking time, if the cost to park is $14? Just make a quick change, make that 16. So I'm going to change it to 16 so we can actually do this problem when we practice finding our intervals, okay? So if I have 16 equals -4, -1/2 x. I divide by -4 to give me -4. And I drop the brackets. I bring this up, so I have -8 equals -x. But these go away. So 8 is my x. So once again, this is my solid dot. I changed the 14 to 16 so we could do this problem properly. Exactly. So if you get a decimal answer as your y, you won't be able to solve, which means the cost cannot be 14. So if we used the 14, just on like a side note, if we used the 14, we would have gotten to this point. And 14 divided by 4 is So we know that this can't happen. So the cost actually cannot be 14. So that's why I just changed this problem. That way we could practice doing our intervals. The negative went away because if I originally here, so if you want to do it the long way, just so we know, I had negative and negative, but then you can't solve for negative x. That doesn't mean much to us. So if I divide by -1, then the negatives just cancel. So just canceling out the negatives on both sides like that is just a way to do it quicker. And once again, this is our solid dot. So to create our step, we need to look at our parameters. So we really only care about b. So b is -1/2. That means b is negative. So my step goes from open to closed. So this is actually the end of my interval. So it's going to be something until 8. If my b is -1/2, my length is going to be 2 because we flip the 1/2. So here I'm going to subtract 2 to give me 6. So I could park between 6 and 8 hours, and it's going to cost me $16. Not too bad. Okay, so the assignment from yesterday, you had you have this. So assignment 8. So you have a couple of step functions. This one's a little tricky, but take a look at it. Same thing here. And same thing here. So really, 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 really try to look at these problems because you can get this. It comes up a lot where you get a step function like this in a part C question. So you don't want to be losing 10 marks because you didn't practice. And same thing here, the forms. You have some practice problems that could come up in a part A or part B kind of situation. Okay, so you now have all the tools to start working on that. The last thing that we have in this set of notes, you have just some quick notes on piecewise. You have everything. The blue is all there. So it's just to give you, again, you're responsible for piecewise functions, just like we did this morning. We did a piecewise function. It involved the square root function and the quadratic function, all that kind of stuff. So piecewise function is a part of this course as well. So you can review some piecewise stuff. Here is piecewise as well. All the different things that you can do with piecewise. And then you also have some notes on periodic, which you're also responsible for. So make sure you're taking a look at those kind of problems. The square root function is what we were doing this morning with this. That's what we graphed yesterday, if you remember. So if you go to the notes from Tuesday's class, you have, this is the picture of the square root function. If you remember, we have the 4 different cases. You're welcome. Okay, so that's it for step functions. So like I said, you should be prepared to have at least one question on this. Could come up in an A, B, or C. So make sure you're going over, especially the assignment and the Google form. Those are like final exam kind of level, what you could expect to have. So make sure you take a look at those, okay? So you have these new notes. What we are going to be doing today is exponential functions. So we're going to start the exponential function today. We're going to continue with the exponential function tomorrow. So you have all the notes of what this should look like, okay? So you did exponential function in this grade 10 CST. So for some of you, that was this year. For some of you, it was last year. So you need to review that. I have included all the notes on it. Ugh, that's a pain. Sometimes it opens without all the stuff I've copied in there for you. So that's a little bit of an annoyance. So what the idea is that we're going to be going very quickly through the exponential function, the basics that you've already looked at, but there are 3 or 4 different things that you may have seen, you may not have seen, but are definitely covered in this class. So those 3 or 4 things are what the new part of the exponential function is for our purposes. So we're going to spend more time doing the new stuff than we will going over the old stuff that you've already seen. So I'm going to go through the notes just quickly to get our brains into exponential function mode, to remember what we're doing. And then we'll talk about the new stuff and the new tools that will help us, okay? So feel free to jump in. I'm not going to be doing many problems with the review, just a couple of quick things to get our brains in gear, but feel free to jump in and ask for clarifications to make sure that you understand this, because again, it is the expectation that you can handle the exponential function and that the new part of this is just whatever we cover that's new. So basic exponential function is y equals c to the x. So we have c as a real number, a positive number. So general notes about c, we call c the rate of growth or decay. C cannot be negative and c cannot be 1. So if we just take a quick look at what this looks like, y equals c to the x. So that's why if c is 1, this is what it looks like, and that's really not helpful for us. But our base case would be c is 2. So this is an increasing function. A little note about the exponential function in general, it gets infinitely close to this axis, but never actually touches it. So this function either always increases or always decreases, which is why we call it a growth or a decay. So it can't be both at the same time. So there are 2 cases for c. So you have these 2 graphs. If you have the increasing case, you have that c is going to be bigger than 1. And if you have the decreasing case, then you have c is between 0 and 1. So again, what this looks like on the graph, here, the bigger c gets, the faster I increase. And if c is 1, it's really super uninteresting for us. And then if c is between 0 and 1, it's a decrease, it's a decay. And if c is in the negative, it doesn't actually work. So you can't have a negative base. So you just have a little table with the properties. But the most important property or the most important aspect of this is that the exponential function has an asymptote. So what an asymptote is a barrier. Think of it as like an electric fence for like on a farm or something like that, where it's like a barrier where you really can't touch it if you don't want to be like electrocuted, right? So an asymptote is like a barrier that the function can get super close to, but can never touch it. So we have this asymptote, and it is the x-axis. So meaning that it gets infinitely close here. So it looks like it actually touches it, but the more you zoom in, it never actually gets to that point. So I could keep doing this forever, but I don't want to. So we're just going to do a couple of these, just remembering how to solve equations when exponents are involved. So we'll do the first couple. So x to the 6, if we remember when we have a number here, when I bring it over, it flips. So we get 1 over 6. So it becomes a fraction. So this is 6 over 1. So this becomes 1 over 6 on the other side. So you type in 64 to the power of 1/6, and you get 2. So these ones, same thing. When you move this number over, it becomes a fraction. So this is 7, it becomes 1 over 7. So 16,384 to the power of 1 over 7 gives me 4. Even if it's negative, it still moves over and becomes negative. It still stays negative, okay? So it doesn't change signs. It just flips. And we remember when we type this in, you have to bracket the 1 over 81 and bracket the exponent, or your answers are going to be completely off. So when I do that, what do we get? We get 1 over 81 to the power of negative 1/3. So we got 4.327. Same thing here. X is equal to 16 to the power of negative 1 over 4. So 16 to the power of negative 1 over 4 gives me 1/2. So just a quick review about solving those type of equations. When you are finding the rule with just C, you need 1 point. Cannot be the y-intercept. The sign, yes, so the side question is the sign stays the same. Yes, the sign stays the same. You just flip the number. So to find the rule with just C, you need 1 point that's not the y-intercept. You plug it in and solve for C. We're not going to do this because 9 times out of 10 you have an A involved, and that's a little bit trickier, so we want to do that instead. But this is just base case, okay? Just to graph, you almost never have to graph, but the rule for graphing is always the same. When you're stuck, you just make a table of values, plot your points. With an exponential, you know the general idea of what it should look like. Like, you're not going to graph an exponential that looks like this. You know what it should look like. So you sketch, you put your points on the sketch, and then you just sketch right through. The transformed function is y equals ac to the x. So you have this extra parameter playing here. So they play different roles. So if we zoom back out here. So notice how you're looking specifically at the y-intercept. When I change the C, it just changes the shape, but the y-intercept never changes, even when I flip it over. But as soon as A comes into play, now all of a sudden I'm changing the y-intercept. And if A is 3, well, the y-intercept's at 3. And if A is 2, well, the y-intercept's at 2. If A is negative, it flips it over the axis, because still A is -2 means that the y-intercept is -2. Because we have these two different things in play, we end up with 4 different cases of the graph. So we have the green, where anything that's above the x-axis, that's when A is positive. So we have the A is positive when C is bigger than 1, which gives us this increase. We have the A being positive and C is between 0 and 1, giving us this decrease. Here we have the flip of the green, meaning that C is between 0 and 1 and A is negative, which flips it over. And blue case, where A is negative but C is bigger than 1, because it is also going that way. Okay. Finding the rule in this form, so just from different points, not from a word problem, you write down the rule, you find the point 0 and something, whatever that something is your A, and then you solve for C. So we're actually going to do one of these. So y equals AC to the x. So you're looking for when x is 0. So that's this point, meaning that is my A value. So y equals 1/6 c to the x. Then I'm going to use one of these points to help me solve for c. So I plug in 500/3 is equal to 1/6 c to the 3. I bring the 6 up. That gives me 1,000 is c to the 3. And we just solved this, so we know that to do this, we take it to the power of 1/3. So 1,000 to the power of 1/3 gives me c of 10. So I can create my rule now. So I have y equals 1/6 10 to the x. And from there, we can solve for different values. But I want to save the solving for different values part until a bit later, because that's something that we really need to look at together. So far, so good. We're remembering everything, or at least it's familiar. Why do you flip the 3/1 to 1/3 when you can just cube root both sides? The definition of a cube root means 1/3. So that's basically, you could do that, absolutely. But you're doing the exact same thing. You're just representing it differently. So you could have said the cube root of 1,000 is c, and you still get 10. It's just a different way of showing it. This means this. That's the definition. So it's the same thing. So now we're going to be solving equations. So there are 2 ways that you learned how to solve equations last year when the variable is in the exponent. So we're going to quickly look at a couple of these. So the first one was matching bases. So what you're doing when you're matching bases is you are saying that each of the different terms can have the same base, changing it to the same base, and then dropping the bases. For instance, I know, okay, I can't solve this. There's nothing I can do right now. But I know that 4 is 2 to the 2. And I know that 32 is 2 to the 5. I can combine these. So I have 2 to the 2x because they multiply is equal to 2 to the 5. If 2 to the something is the same thing as 2 to the something, those somethings should be equal. So I could say 2x equals 5. So x is 5 over 2. So you match the bases, and then you drop the base to just solve the exponent equation. So we'll do one more. There's nothing I can do, but 81 can be written as a power of 3. So 81 can be replaced with 3 to the 4. And 729 can be written as 3 to the 6. I can combine these by multiplying them. That gives me 3 to the 8x is equal to 3 to the 6 times x plus 5. Because I have the same base, I just take the exponents and I solve that equation. So 8x is equal to 6x plus 5. Moving here, I get 8x equals 6x plus 30. If I bring this over, I get 2x. And I divide by 2, giving me x is 15. So that was the matching basis. So you did this during the year. You still have to know how to do this. This could come out as a part A, part B question. So you want to make sure that you can handle those type of equations. And in your handout for today, there are a lot of those. But this brings me to the next point. Okay, so this is where we're starting to get into new material. So last year, your second method was to guess and check. So when you got to the point where you had these equations, you would start typing in different values for the exponent. So I'm going to guess 2 to the 3. 2 to the 3 is 8. And then I guess 2 to the 7. That's 128. So it's going. So I guess 2 to the 9. Oh, I got it. So 2 to the 9 is 512. So x is 9. So you had to sit there with your calculator and just guess different things because we didn't have the tools to access this exponent because we didn't know how to invert an exponent when it was a variable. So when it's a number, it's simple. We bring it to the other side and we flip it. But when the exponent is the variable, that's when we have an issue. So let's talk about the inverse, the opposite of the exponential function. So this is where we're talking new stuff here. So we talked about inverses. So I know with inverses, I switch these two and I try to isolate the y. So I get x equals a, c to the y. I divide by a. So I get x over a equals c to the y. Now, I don't have the tools right now to access this y, to find some way to drop it down. So the issue is, how do we reverse the exponent when the exponent is a variable? So I'm about to give you the tool to do that. But graphically speaking, remember when we find the inverse, that we are flipping it, we are reflecting it over x, the y equals x line. to create our new picture. So if we are looking at this, this is what it would look like if we sat there and we reflected it. So here we have the 0, 1. So we have the 1, 0. We have the 2, 4. So we have the 4, 2, and yada, yada. But as it turns out, this thing is a function that has a rule. We call this the logarithmic function. It is the inverse of an exponent. It is, however, considered an exponent itself. So if you decide to do the TS course next year, you're going to see the properties of logarithms and how you have the same type of idea. You have the properties of exponents. And because logarithms is a reverse exponent, you end up having your own properties for that. The thing we notice is this has an asymptote at y equals 0. So it's getting, notice here, it's getting infinitely close to the y-axis, but never touching it. It's the same thing as this function getting infinitely close to the x-axis. So we have this relationship. Oh yeah. So we call this a log. So on every scientific calculator, you have the button that says log. You've never used it. Well, we're going to use it. So the inverse, like I say, y negative 1, is equal to log base c. So we call this the base of x. So notice that my base is c and my base is c. So the bases don't change, but it allows us to access this. So instead of solving, we just actually have to do this flip. And it's going to help us when we're solving equations. So we're just going to find the inverse just using that relationship back and forth. So we don't really have to do anything. We just have to follow this rule. So it says that the inverse is going to be y equals, we have the log with the base as the same. So this is the base. And the exponent becomes the input. So if you try to just click log equals on your calculator, you should get an error because log needs something on the inside. It's not just a something by itself. It's like if you click sine and you just get, you have to actually put something in the sine or the cos and the tan to get an answer. It's the same thing here. So we use the same relationship. So I have a y equals log 12 of x. So let's look at this one. It's actually reverse. So the inverse, we're going to be using this relationship backwards. Says y equals, we have 15 as our base, and the x goes back as the exponent. And if we look at D, and by D I mean F, you get y equals, the base is the base, and this pops in as the exponent. So these are inverse functions of each other. Now, why does this help us? This helps us because there is a better way to solve exponential equations that doesn't involve us having to sit there and guess and check until we figure out the answer, or at least approximately the answer. So this gives us a way of solving exactly the answer without having to guess and check. So this is a super important relationship. So this absolutely needs to be on your memory aid. So when I have a number equal to some base with x as the exponent, this changes into x, the exponent drops. We have log of this side divided by log of the base. Okay? So we're going to use this relationship and flip things over. So when you have the number on the bottom, that actually means the base. So this allows us to solve equations precisely. So what we are going to be doing is we are going to manipulate the equation so that way we are left with what we recognize. So here we want to be left with the something to the exponent equals something. So this is what you are working towards. So you know how we did the greatest integer algebra when we had to isolate the greatest integer bracket? Now you have to isolate the exponent term. You're then going to use your log relationship to switch it over so we can access this. And then you're just going to type it into your calculator. So everyone should have their calculator out right now because you really need to practice using this. If, just on a general note here, if you just try to use your calculator, the calculator has a default setting of base 10. So if you type something in, what it's actually doing is saying you're doing, let's say you type in log of 27, what it's actually doing is putting it in base 10. Okay, so you actually need to put a number here, otherwise it's going to default to 10. So we're going to do some of these problems just to practice here what this relationship looks like. So here, step 1 says I need to isolate the term with the exponent. So I did. Now I'm going to change it using my log relationship. So I have a equals c to the x. So x equals log of a divided by log of c. So I'm just going to write this in color. A log a, c, and x. So we're going to use this relationship to flip this around. So just underline it. This is my A. So this should have been blue. This is my A. This is my base. And this is what's going to drop. So this drops on its own. Then I get log of 48 divided by log of 2. So you're going to type that into your calculator. So you get log of 48 divided by log of 2. So you should get 5.58. So when you're guessing and checking, you're never going to get an answer this precise. You'd have to be working on your guessing and checking all day to get an answer that precise. So this helps you solve those problems if your answer isn't perfect. So you're always using this relationship. So we're just going to keep dragging it down. So let's try the next one. So I've got, this is my A, this is my C, and this is the X. So purple drops down to its own. Blue goes on the top. And red goes on the bottom. So don't worry about this for now. Just type this into your calculator because it's going to give you a number. So I say log of 1,000 divided by log of 5. That gives me 4.292. And then all I do to solve for x is I divide that by 2, and that gives me 2.15. So again, you're never going to get an answer that precise just using your guess and check. So this is just another tool. So this especially should be on your memory aid. And it helps if you use the colors to match things up, and then you can do that when you're changing things over.
Miss?
Yes.
Is that formula on the mock memory aid?
Yeah, I believe so, yes. Let me just check it. It's a good question. If not, you have it. Yeah, it's right here. Right at the top. But it's written a little differently than what I wrote it. So the way I'm writing it is actually putting those two. So it's putting this equation together with this. So you only do it in one step. So just something to think about. All right, let's try another one. So I have my A is 1/2. My C is 64 and my exponent is X. So the X drops by itself. The A term goes on top, making sure you bracket, and the 64 goes on the bottom. So log of 1/2 divided by log of 64 actually gives you, says repeated. Yes, you can use it as a fraction. So you could say log of 0.5, that's fine. Let's do a couple more just to make sure we're comfortable with this, because this is going to be such a useful tool for exponentials. All of a sudden, the guessing and checking nonsense is gone. So we've got our A, we've got our exponent, we've got our base, we switch it up. X equals log of 19683 divided by log of 1/3. In this case, because it's not a perfect decimal, please, please, please use it as a fraction. So you have log of 19683 divided by log of 1/3, and you get X equals -9. How do we feel about this instead of guessing and checking? So this is just a way faster, simpler, more straightforward way of doing this. The key is making sure you have this on your memory aid and that you really know how to flip it around. So on your assignment for today, you have a couple of practice word problems. So you've got these, we're not going to go over it now because class is pretty much over. But you have these practice word problems. So word problems is something you covered last year. So you just got some practice here. We can start with one of those problems tomorrow. But the assignment that'll be popping up soon is practice on that and a lot of practice on the log functions. Make sure you take a look at that. And then the handout that will be popping up in about 5 minutes has a lot of the practice with log functions. Okay, so make sure you take a look at that. And then we'll continue on with more exponential, finishing it up in the first half of class tomorrow. If there are any more questions, send me an email. Other than that, have a good afternoon, and I'll see you tomorrow.
Have a good
Thank
afternoon,
you.
Miss. Bye.
Thank you.
Thanks.
Thank you.